we spent quite a bit of time in this class talking about the motion and energy of single object systems. In this mini unit, we are going to actually talk about what happens when we have more than one object in our system and they undergo a collision. Okay, so here I've drawn, this is a football player, if you can't tell by my drawing. Okay, but looking at a tackle that happens in football, like speed, the velocity at which the person is coming in, or their size makes a huge difference, okay, in kind of the outcome of the collision between the two players. So football players want to be big and fast, okay? That helps them kind of win a collision in football, okay? So when we're looking at, if we define this two football player system, okay, looking at the collision, the two players are coming at each other. They both have probably some kinetic energy, and if they're fast, they might have quite a bit of kinetic energy. But after the collision, usually they're like stationary right after the collision. A lot of times there's not as much kinetic energy. Okay, it's not like they're flying after the collision super fast. So when we look at kinetic energy would not be conserved in a collision like this, in a tackle. So what is conserved when we're looking at this two object system? Well, something called momentum is what's conserved. Okay, so momentum is conserved in a collision like this. If there's no external net forces acting on what we've defined as the system, if there's only internal forces, so the forces between the two players, those are internal to the system that we've defined. Okay, so what I originally said was that like football players, they want to be big and fast. So we kind of have an intuitive sense of that guy had a lot of momentum coming at him. Okay, well, momentum we define in physics as equaling mass times velocity. Okay, and that makes sense. Football players want to be bigger and they want to be faster. Okay, so this definition here is the definition of momentum. It's kind of weird that we use a p, but m was already taken by mass, so p is actually our variable that we use for momentum in physics. Okay, it is a vector. Okay, and that's important because when we look at adding momentums together, you have to pay attention to what directions it's in. So you have to break things into components, like we did when we were doing our kinematics unit. So remember that momentum is a vector, and that makes sense because velocity is a vector. Okay, so the momentum vector is going to point in the direction of the velocity of the object. Okay, this is specifically linear momentum. Basically, if you hear the word momentum, it's kind of assumed that we're talking about linear momentum as opposed to something called angular momentum, which we might later touch on in this class. But for now, we're just going to call this momentum. And so a pretty simple calculation. So let's look at just a one object system, and let's say we were trying to calculate what the momentum of a certain object is. Okay, so I'll keep it so that we can see our equation. So let's say we have like a billiard ball, or actually this is kind of big for a billiard ball, a 1 kilogram ball moving on a horizontal surface to the east at 6 meters per second. Okay, so let's establish a reference frame here. Let's say we're doing like north, south, east, west. Okay, so this ball, we would calculate the momentum by taking the mass of the object times its velocity. So we take 1 kilogram times 6 meters per second, and we get a momentum equal to 6 kilogram meter per second. Okay, so the units of momentum are kilogram meter per second. Okay, so we got the units of mass, kilograms, and then you just say kilogram meter. I like to put a dot in there so you know that the M isn't part of the kg unit. So kilogram meter per second are going to be our units of momentum. Okay, and specifically when we were to report this momentum, we would have to say a direction. Okay, so to the east, let's say, for this this ball that was moving. To the right. If we said to the right is the east direction, we've reported our direction. So we could also have a positive and negative direction. It just depends on how you set up your reference frame. I chose to use north, south, east, west as my reference frame. Okay, so let's look at another example. So let's say we have a 2 kilogram ball, in this case, that's moving it to the east at 3 meters per second. Okay, so if we calculate our momentum in this case, mass times velocity, we have 2 times 3, and we get 6 kilogram meter per second. Okay, so here we had a ball that's more massive, but its velocity is less, but they end up, because this one is also going to the east, they end up with the exact same momentum. Okay, but let's say that instead this 2 kilogram ball was moving south at 3 meters per second. Okay, it's still 2 kilograms. We calculate the momentum. 2 times 3 equals 6 kilogram meters per second, but this time it's to the south. So this is actually, because direction is a part of momentum, this is not the same. Okay, because it has a different direction. Its magnitude of its momentum is the same as we're talking about this one up here, that example. Okay, so the magnitude is the same, but if the direction is different, then we can't say that they have the same momentum. You can say the magnitude of their momentum is the same, but they don't actually have the same momentum. Okay, when we're looking at our system, okay, up here I said momentum is conserved. So what does that mean mathematically? Okay, what that means mathematically is if we look at the total momentum of a system, let me change colors here. So if we look at our system, okay, and let's say we have 2 objects, object A moving with a certain velocity VA, and an object B moving with a certain velocity VB. Okay, if we were to look at this system, the total momentum is conserved. Okay, if we have no external forces acting on the system, no net external forces, then the initial momentum, the total initial momentum, so we'll call that P total initial, is going to equal our final total momentum. Okay, so we'll call that P total F. Okay, so this is an important equation here. Okay, if we have just 2 objects that we're looking at, this equation would become, well, we look at the momentum, so MA VA initial, this is a vector, plus the mass of B times the VB initial equals the mass of A times its velocity final, so that's an F there, plus the mass of B times its velocity final. Okay, so this is a simplified version of just kind of writing out the momentum of each of the individual objects in the system. Okay, when we're looking at this momentum is conserved, we're looking just before the collision and just after the collision. Okay, just before and just after. We're not looking during the collision. We're saying it's a pretty short collision, But when we're defining these initial and final time points, it's just that millisecond right before the collision and just right after the collision. Okay. So let's take a look at an example and apply this equation. So let's say we have a person on their longboard. So here's an example. Okay, let's say we have a person on their longboard. Okay, and they're currently neither them or their longboard. So we'll say the person equals 0 meters per second, and v of the longboard equals 0 meters per second. And this is our initial system here. Okay, so this is initially. Okay, but then the person decides to jump off the longboard. Okay, and they jump off their longboard, giving themselves a velocity of 0.5 meters per second. Okay, and the longboard, if you've ever done anything like this, is going to shoot off in this direction with probably a much higher velocity. So we'll draw, that's a terrible arrow. We'll draw a longer arrow here. Okay, so this is our velocity of the person final. Okay, and our velocity of the longboard final, we don't know. Okay, but let's say we know the mass. So this is our final right after our, well, we're calling them collisions. This is kind of like an interaction between the two objects, but we can qualify this sort of as a collision. So here's our final condition there, just after this person jumps off. Let's say we know the mass of the person. Okay, like we know the mass of the person equals 60 kilograms, and we know the mass of the longboard is 3.0 kilograms. Okay, so let's set up our conservation of momentum equation. Okay, if we write it out, we have the mass of the person, and in this, we're assuming usually when we do these conservation of momentum that the mass stays the same. So that's why I don't have an initial and final mass, because we're saying that the mass stays the same. So we have the initial velocity of the person plus the mass of the longboard plus velocity of the longboard initial equals the mass of the person times the velocity of the person after they jumped off. So we'll call that F final, plus mass of the longboard times velocity of the longboard final. Okay, well, a couple things are going to become 0 for us. So both the longboard and the person initially have no velocity. So that actually makes both of these terms 0 here. Okay, so 0 equals, well, our mass of our person we know to be 60. Okay. The velocity of the person final, we know is to the left. Okay, well, I was kind of careless here. I need to set up a reference frame. So let's call this our positive X direction and this our positive Y direction in our picture. Okay, and so now we can say if their velocity in the picture that I've drawn is to the left, that's a negative 0.50 meters per second, plus the mass of the longboard we said was 3 kilograms. Okay, and the velocity of the longboard, that is what we are trying to find. Okay, so this is great. Now that we've set up our equation, we actually only have one thing that we don't know. That's the velocity of the longboard after the person has jumped off. So we take 60 times 0.5, that's negative 30, plus 3 V longboard final. Okay, and we get 10 meters per second is equal to our velocity of the longboard final. And this happens to be in our positive X direction. Okay, and I've made it a positive number, but I'm just going to be really specific there and show you that I have reported my direction. So the velocity of that longboard, if you jump off and you're 60 kilograms and you give yourself a velocity of 0.5 meters per second, your longboard is going to be going 10 meters per second in the opposite direction, in this case, in the positive x direction that we established. Okay, so there's an example of how you can apply our conservation of momentum equation. Okay, when we look at these problems, it's important to know, I said that this applies our conservation of momentum, our P total initial equals P total final. This is going to apply when there's no external forces. Okay, acting on our system that we've established. Okay, in real life, if we look at things like billiard balls colliding on a pool table, or if we look at two cars crashing, and apologize for my terrible artwork here. Okay, let's say we have two cars coming at each other that are going to crash. Wow. Okay, two cars that are going to crash. We do have friction forces and air resistance acting on these. So technically, it's kind of hard to say that there's no external forces. But if we think about it, if we talk about our conservation of momentum in the split second just before these cars are going to crash, okay, so let's pull this guy over. So if we look just before these guys are going to touch right here, well, the forces that act in the collision, forces acting in the collision, are way higher. So during collision, forces are way higher. And specifically, these internal forces are way higher than any friction forces. So than any external forces, like friction forces between the car and the ground. So we are okay if we're looking just at our conservation momentum just right before the collision and just after the collision, because those internal forces are way higher than the external forces, we can still apply our conservation of momentum equation. Even if there's small like friction forces that otherwise would be important, if we're looking at a collision with high impact forces between the two objects, it is okay to kind of assume that those external forces are negligible during the time with which we're analyzing the situation. Okay, so let's take a look at an example with billiard balls. Okay, so this will be our second example that we're going to look at. So I'm actually going to scroll down here. Okay, the first example we did just involved one dimension. So let's do one more example looking at conservation of momentum where we have more than one motion in more than one direction. Okay, so let's say we have a billiard ball, and we'll just label it A. And let's say it has a mass of 2.5 kilograms. And initially it has a velocity of 2 meters per second, headed right at billiard ball B. And for some reason, billiard ball B has, for some manufacturing defect or something, a slightly higher mass of 0.3 kilograms. Okay, so this is initially what's going on right before the collision. Okay, and remember we said I'm not going to draw it like right before the collision, but know that our conservation of momentum equation works just for right before the collision and right after the collision. Okay, I got to draw it so you can see they're a little bit further apart, but really this is like right before they collide. Okay, and then after the collision, we know that billiard ball A takes off at 1 meter per second. Okay, or it gets deflected 1 meter per second, traveling 30 degrees above its previous direction. Okay, and we want to know, where does billiard ball B go? We kind of intuitively know it's probably going to go somewhere in that direction, but we want to know what that VB final is. Okay, we do not know. Okay, so this is our final right after the collision. And we're trying to find what is that velocity of billiard ball B right after the collision occurs. Okay, so because our momentum equation here, we're dealing with vectors. Okay, what we're going to have to do is we're going to have to split and do kind of two analyses here. And we'll analyze in the x direction with our conservation of momentum, and that should give us our velocity bx final. And then we'll do another analysis in the y direction to give us what the component of that y velocity is right after the collision. And then we can come back and we can figure out what our overall magnitude and direction of that velocity vector is. Okay, so let's take a look at the x direction first. So our x direction, okay, so we have to do an analysis in the x direction, and we also have to do an analysis in the y direction. Okay. So let's start with the x. And my x is in blue. I am in blue already. So we have our px initial is going to equal, well, our p total, our total momentum. I forgot the total. Total x initial is going to equal our total x final. Wow, folks, I'm having trouble writing today. Total x final. Okay, so well, let's write that out. What does that mean? Well, it means our mass of the ball A times VAX initial plus mass of B times VBX initial equals mass A VAX final plus mass of B times VBX final. Okay, so looking at what we know that billiard ball B is not moving initially. Okay, so that whole term becomes 0. Okay, we know the mass of A, we know the mass of B. Okay, we know the initial velocity of A and the x, and we actually know the final velocity of A and the x if we do a little bit of trigonometry. So let's go ahead and look at that. So we plug in our numbers. Well, 0.25 times 2. And y'all, I didn't establish my reference frame again, but let's say that this is our positive y, straight up and on the screen, and straight to the right is our positive x in our reference frame. Okay, so we have 0.25 times 2 equals 0.25 times, okay, here's where we have to do a little trigonometry. We know after the collision that our billiard ball A is traveling at 1 meter per second, 30 degrees above where it was traveling before, so 30 degrees above our positive x direction. So if we want to solve for this x component, right, we can't use 1, we have to use this x component, v ax final is going to be that component right there, and it's adjacent to that 30-degree angle, so we know that's going to equal 1 times the cosine of 30. Okay, so because we know cosine of 30 equals VA XF divided by 1, we just multiply both sides by 1, and that's what we get. Okay, so 0.25 times, well, the 1 is just 1, so we'll write it anyway, but we could just ignore that there's a 1 there because 1 times cosine 30 is still cosine 30. Plus, and we know the mass of B is 0.3, and we don't know VBX final. That's what we're trying to find. But fortunately, this equation, we know everything else in this equation. So when we solve for VBX, so we multiply these together, multiply that together, subtract and divide by 0.3, and we get 0.94498 as the value for our VBX final. Okay, so we're halfway there. We know VBX final now. Okay, hopefully setting up our momentum equation in the y direction is going to help us solve for the y. Well, I know it will, but let's be hopeful too. Okay, so we got p total in the y initial equals p total in the y final. Okay, our full equation looks very similar to our initial one. I'll draw a line here so we can kind of distinguish between the two sides. So we have mass A, VAY initial plus mass B, VBY initial equals our final. So we have mass A, VAY final plus mass B, VBY final. Lots of subscripts here. Okay, so just like in the x direction, we have no velocity of billiard ball B to begin with, so that whole term cancels out. Okay, we have, actually in this case, take a look at this. Our A had 0 y velocity, so this term actually cancels out as well, because the velocity in the y is initially 0. After the collision, however, there was some y velocity. Okay, so we are going to need to solve for VAY final, and that's opposite of that 30-degree angle, so we end up with 1 times the sine of 30 degrees. Is going to be what our final y velocity for billiard ball A is. Okay, so we have 0 equals mass of A is 0.25 times 1 sine 30 plus 0.3 times VBY final. Okay, fabulous. We now have everything in this equation except for VBY final, which is what we're trying to find. We end up getting a negative 0.125. Okay, we multiply that and subtract it from both sides, divided by 0.3 equals VBY final, which is a negative negative 0.416667 ish. Okay, so now we actually know both of these. Okay, so let's redraw our final situation here with billiard ball B, and plug in the components to solve for the actual. I mean, we could report that it had an x component of 0.945 and a y component of negative 0.417 for its velocity, but let's be complete here and talk about, okay, what this actual magnitude of velocity B final is. Okay, and we can and its direction. So we want to find this angle as well. Okay, so we know our two components, right? We know that we have this component is 0.94498, and our y component, we're going to move this over to here. Okay, so then I can draw my y component in there. Okay, my y component I know points downward because it's negative. 0.416667 is what I wrote down. There was more decimal places in that, but that should be sufficient. Okay, so, oops, I made this green. This is what we're trying to find. It's supposed to be white, turned green accidentally. So, how do we find the magnitude? Well, we take the square root of 0.94498 squared plus 0.41667 squared to get our we're solving for the actual magnitude of the velocity. And that ends up being 1.03 meters per second. And then we can solve for our angle theta by taking the inverse tangent of 0.416667 over opposite over adjacent 0.94498, and we get an angle of 23.8 degrees. below the positive x direction that we established. Okay, so that is our answer for the magnitude and direction of this billiard ball B after they collide. Okay, hopefully that was a helpful example to kind of look at. There you go. I'll give it so you have everything on one screen. And it ends up being a little bit more work, but it's pretty simple. Our equation is just m times v, and you have to solve it though using vectors. You have to split it into the components and solve the x components and the y components, and you can bring it all back together at the end because momentum is a vector. Okay, but really all we're doing ever is we're just multiplying mass times velocity for each of the individual components, and the total initially is going to equal the total final for each dimension, the x direction, y direction, and if we had a z direction, we could add a z direction. I don't think I'll do that to you though. Okay, yep, I hope this was helpful, and thanks for watching.